So physical quantities, what is a physical quantity? It is something which can be measured. For example, length of this marker or mass of this marker. Length of this marker, as you can see, it is something like uh, 15 centimeter, and mass is about 20 gram. So when I look at this and this, what I see here is I see one number and one unit, a number and a unit. Now what is the need for a unit? Need for unit is, okay, I'll give you an example. I get a purchase order from two companies, one in US and the other in Japan, and the order is for supply of shirts for average males, right? So now what I do is, my delivery time is about 20 days, and in this 20 days I have to manufacture 1,000 shirts each for this Japan and US order, and I supply the goods, and a week later I receive emails for rejection of the goods from both the companies in the US and in Japan, both, and that is a huge loss for me, right? Now I try to analyze the problem here. The order was for average male, okay, average male, aged about 30 years, and I supply. But then the problem was in India, average height of Indian males, it is 5 foot 6 inches. In Japan, it is 5 foot 2 inches approximately, and in the US, an average male, his height is about 6 foot and 5 inches, something like that. I'm not sticking to the exact values over here, but then what is to be seen here is this number differs from both these numbers, correct? So what? So now here comes the need for a good unit. That is when people define unit for length as meter, unit for mass as kilogram, unit for time as second, and so on. So that is how units were needed to be specified. A unit should be such that it doesn't change from place to place. In India, if 1 meter is so much, in the US it will have same length. In the UK, it will have same length. It doesn't change from place to place, right? So now, so that was about units. Now let us try to see what are fundamental quantities and then derived quantities. Now, fundamental quantities are the physical quantities which do not depend on any other physical quantity. Like, let us say length here, then mass, time. For specifying length of an object, I don't have to depend on any other physical quantity. For mass and for time, right? But then if I think of velocity, or if I think of frequency, right? If I say velocity here, what is the unit of velocity that we use for so when I'm driving my car, the speed that I see on the speedometer, it is indicated in kilometers per hour. If I try to find pressure, unit of pressure is Pascal, and 1 Pascal is equal to 1 Newton per meter square. When I think of force, my force is equal to mass into acceleration, but I define my unit of force as 1 Newton, and 1 Newton is nothing but 1 kg meter per second square, and that is because my force is equal to mass into acceleration. Now you can see here my velocity depends on the distance and time, my pressure depends on force and area, my force depends on mass and distance and time. These physical quantities which depend on the fundamental quantities like this, these are derived physical quantities, and these are my fundamental physical quantities. But now, apart from length, mass and time, there are 4 more. What are they? One is temperature, second is current, then there is amount of substance, and the last one is luminous intensity. Now here, let us try and write the units for them. Length is measured in meter. My temperature is measured in Kelvin, absolute temperature. Then mass in kilogram, current in ampere, time in second, amount of substance in mole, luminous intensity in candela. These are the fundamental quantities. Right? Apart from these 7 fundamental quantities, there are 2 more additional quantities, that is this plane angle and solid angle. Unit of plane angle is radian and unit of solid angle is steradian. These 2 quantities we will be we'll talk about these 2 in detail in in the sessions to come. For now, fundamental and derived quantities. Now let us talk about I have already mentioned these units of these quantities. The units of fundamental quantities are called fundamental units, and units of derived quantities, they are called derived units. Now coming to how to have different systems of measurement. As I said some time back, we have SI system. SI is the system of units given by System International. Then there is CGS. Apart from SI, I have CGS system. And then there used to be this British system that is called FPS. So this is foot pound second, this is centimeter gram second, and here I have SI, SI fundamental quantities, that is length, mass, time, then current, temperature, amount of substance, and luminous intensity. Okay. Now, how do I convert? How do I convert units from one system to other? For example, I have 1 meter is equal to 100 centimeter. So when some quantity is expressed, some length is expressed in centimeters, for converting that into meter, what I do is I divide it by 100. Or if I have been given some quantity in meter and I have to convert it into millimeters, then what I'll do is I'll multiply it by 1000. So centimeter, millimeter, this is micrometer. There are different small and large units. Let us see what it is. So when I have milli, then I divide by 1000. When I have centi, I divide by 100. Then I have micro, I divide by a million. When I have nano, I divide by a billion. When I have pico, I divide by 1000 billion. That is 10 raised to power 12. I am dividing by 10 raised to power 12. So I am writing 10 raised to power minus 12 here. So now these are smaller units. What about larger units? When I say kilo, I am multiplying by 1000. When I am having mega, I am multiplying by 10 raised to power 6. I am multiplying by million. When I have giga, I am multiplying by a billion, and so on. So these are different factors or powers. We are using powers of 10. Actually, when we use powers of 10, it is easier for us to express a physical quantity in very conveniently, right? It's very convenient using the units and numbers. After that, there is something called order of magnitude, which I would like to discuss now, and that is going to be the last part of this video. Now, first of all, what is the need for expressing order of magnitude? For example, there is this building where about let us say 100 flats are there, and in each flat, average 5 people stay. So that means 100 multiplied by 5. So total number of people would be 500. But can I be very sure that in this particular building at some point of time, at some given point of time, 500 people will be there? I'm not very sure. In one flat, maybe I have only 2 people. One flat may be locked. The third flat, there may be 7 people over there. I'm not very sure as to exactly how many people are there in any given flat at any given point of time. But still, some emergency takes place over there, and then I have to express or estimate how many people are there in that building. For example, in case of fire, how many people are there in the building? Someone asked me. So what is my answer? So I would say there are about 500 or maybe hundreds of people are trapped in the building. That would be my answer. There is maybe a big fair on some big ground there, and I would say thousands of people are there. So when I say thousands of people, I am not sure about the exact number, but still I should be able to quantify the number, right? So that is the utility of order of magnitude. Now here there is some logic used for expressing these physical quantities. Now, for example, I'll give you one example of mass of Earth, and that is about 6.0 into 10 raised to power 24 kg. Now, how do I express it? How do I express order of magnitude of this? Now, for order of magnitude, suppose I have this number n here, and that is equal to a into 10 raised to power b, correct? And here the condition is a should be greater than 1 over root 10, and it should be less than root of 10. Now, why this root of 10? If you find root of 10, square root of 10, so here 10 raised to power half is equal to 3.162 approximately. It is 3.16177 something, but then I am approximating it to 3.162 here. Okay. Now 10 raised to power 5 is 10 raised to power 0.5, so that is 3.162. But when I round off my digits, this 0.5 would be rounded off to 1, correct? So whenever I have something like this, I would call it approximately 10 raised to power 1, and that is the logic behind this. So now here my 0.3162 less than or equal to a, and less than it would be 3.162. So my actually, I should be expressing a given number in this form such that value of a lies between these two numbers. Now over here it is 6, and then my a has to be less than 3.162, right? So then what I'll do here is I'll write this as 0.6 into 10 raised to power 25 kg. Now it fits into this form. So order of magnitude of mass of Earth would be 10 raised to power 25 kg. So this is how we would be approximating these orders of magnitude. I'll be giving you a few exercises for this in the next video.